Thank you very much for the introduction. My name is Okura from Yahoo, Japan. I am near 12th machine learning black belt at our company. I joined the company in 2012. I was the system engineer for advertisement-related system. I am now researcher developer for the news recommendation. In 2016, we introduced the first deep learning model for news recommendation to Yahoo Japan top page, and since then we have continued to improve the model in parallel with user analysis. So we're going to talk about our system and also the challenges we face. First, I'd like to give you an overview of our system, and then I'll cover the three topics, which are the challenges we face right now. First of all, this is the top page of Yahoo Japan app. At the top of the page are 6 top news stories called Yahoo Topics, selected by editors. This is a human selection process, which of course provides high-quality articles, but it does not necessarily mean that articles are selected according to the interests of each user. So if you go down a little bit, taking into account the user's preference, the recommendation system allows to see the list, the articles optimized for each user. Today's main topics are how this module is implemented and what challenges that we are facing right now and how we are trying to solve these problems. First of all, I'd like to give you the overview of recommendation system. First, I'll discuss some important concepts in news recommendation. Among recommendation systems, a particularly important concept in news recommendation is immediacy. When information is updated in a news article, older articles are no longer useful. Therefore, it is important that posted articles become eligible for recommendation as soon as possible. For example, it is not appropriate to create a recommendation list for each user in advance and display it when the user visits the service, because news posted between the time the recommendation list is generated and the time the user visits the service will be dropped from the list of candidates. Also, methods that rely heavily on the click history of article, such as collaborative filtering, are also undesirable. In this case, two articles are not recommended immediately after they are posted because they have no click history. Therefore, we are trying to create a recommendation list from the latest article inventory at the moment a user visits the site, while reducing amount of computation to minimize latency. So this is the overview of our system. This system can be divided into two major parts. The left-hand side, which is pre-calculated before the user visits, and the right-hand side, which is calculated on the spot at the moment user visits. In particular, note that parts of the model involving complex machine learning models are placed in the pre-calculation part on the left-hand side. So let's have a closer look. In the lower left part, user features are extracted from each user's activity log, converted into a vector, and stored in KVS with the user ID as the key. This process does not need to be done in real time, but rather in batch processing several times a day in a distributed computing environment, since the user actions in this session should be reflected in the next session. In the upper left, posted articles are analyzed, converted into feature vectors, and indexed into a vector search engine. Although this is performed sequentially each time an article is posted, it can be calculated in advance independently of user usage. In addition, the number of views immediately after an article is posted is estimated and included in search engine as one of the feature values. Although the result of article views has a strong feature, there are no result for articles immediately after posting. So we supplement this by estimating the number of views. So preparation of users and articles information is finished. We wait for the user to visit. So when a user visits the service, retrieve the user's feature vector from KVS using user ID as a key, a request is then made to the vector search engine as a query to obtain a list of articles that are close to the user vector and add the duplication to the list, and the list of recommendation to the user is complete. Since the actual calculation after receiving a request from a user is almost exclusively similar vector search, the result can be returned at high speed. The user's behavior is fed back as a log, and time the user next used service will be reflected in the user history and incorporated into the features. In addition, the result that was supplemented with estimate immediately after posting will be corrected with the actual result once the logs are collected. And after this loop runs for a few days, each model is periodically retrained using the data accumulating during that time. So this is the basic flow of our recommendation system. Next, I'll discuss how the machine learning models used in the system are trained. Although three models are depicted in overall diagram, we will focus on the two models that extract feature vectors. These are the models that vectorize articles and model that vectorizes users. They need to be trained simultaneously because eventually the user vector needs to be able to retrieve article vectors using the user vector as a query. These models are trained in two steps: pre-training using only article data and main training using article data and user behavior history data. Initially, a language model is trained to interpret articles written in natural text using a large amount of article data. Next, features of articles created by the pre-training model and are input into a model that aggregate user behavior to perform fine-tuning of the article vectors and learning of user vectors. So I'd like to give you a little bit more in details. So in the pre-training phase of learning a language model, the BART model, which has probably appeared several times at this event, is being trained. The BART model is a general purpose corpus, and while there are several pre-trained Japanese models are distributed, since there is enough data of news articles posted to Yahoo Japan in the past, we use them to train the model from scratch. So we input the headlines and text of the news articles and let the familiar masked language model and next sentence prediction solve the problem. Once the language model has been acquired to some extent, next step is to move on to the main learning process using user behavioral history. Here, the user's past browsing history is converted into a vector sequence using the aforementioned BART model. This is then passed through the current neural network and aggregated into a single vector. Metric learning is performed between resulting user vector, the vectors of positive articles actually clicked out on at the time of the recommendation, and the vector of negative articles that were recommended but not clicked on. So metric learning is performed to optimize the RNN part and part of the BART so that article retrieval using the user vector as a query works well. By using an RNN that takes into account the order of browsing rather than just averting the user history, we were able to improve the number of the clicks by the amount of 10%. This is an overview of the recommendation model that we are currently operating. So in the remaining time, I'll present 3 examples of issues we have been focusing on recently related to recommendation systems and how we try to solve those.
So first one is the diversity of the recommended content. So for all the diversity, we do not give a particular consideration. So we are going to apply the previous day article, and if we do the recommendation based on the user record, then we are able to come up with this kind of a list of the article. And there are two reasons why we come up with this list. So first one is we are handling the multiple articles that are coming from the multiple resources used by the Yahoo Japan. So if there's a certain news happening in the society, then there's a multiple media that writes about the article and posts the article. So as an inventory of the article at Yahoo Japan, we have a similar articles, but coming from the different medias. So on top of that, the second reason is the similar vector search-based recommendation is to be created. Then the score of that article, based on the contents of the article and the interest of the user, is going to be reflected. So based on the distance of the user vector, the recommended article is going to be decided. So there's a similarity for the article, then it's going to be close to the embedded article. So the score is going to be similar. So once the similar article comes in, then the similar score is going to be placed. So the similar article is going to be lined together in the list. So after doing the similarity vector search, then we need to deduplicate. So for this issue, we tried two approaches. The first approach is based on the similarity between the article vectors, so we make decision about the duplication. So as shown here, the duplicated contents. There are vectors which is similar to duplicated, then it's going to be quite similar. So we measure the cosine similarity, and if it's 0.98, if it goes over a certain threshold, so rather than placing the two articles, but we are going to skip one and show in the list. And another list is called using the clustering. So in advance, we divide the cluster of the article in separate types, and based on that, the content shown, if there's certain orientation to a certain type of article, then in this case, there is a series of the articles in the same cluster. So after the certain lines, then we can skip the same type cluster. So compared against the first approach, so it's a more rough granularity. So we are able to prevent the similar article for the whole list. So by combining the two approach, we are able to confirm a certain effect. So the duplicated article, so we are able to prevent showing the same article, and we are able to increase the number of clicks based on that. But there is a limitation to these two approaches, or the combination of the approach. So if the duplication is only limited to a few articles, but if the interest of the society is high, then the similar article can be hundreds. So hundreds of similar articles can be posted. So even if we are able to skip the duplicated one, so if we set the threshold at 0.8, then we are able to skip the similar most of the similar contents, but out of the a few hundreds, so for many articles, then it is going to be within the threshold with a slim margin. So from the user perspective, so users do not understand there are many articles being skipped here. So from top to bottom, they see the similar articles to be listed. So in this situation, we took next one. So it's a re-ranking based on the distribution. So based on the past method, so article, the X score. So what kind of articles are listed beyond that article is not being considered. So based on the contents of the article and the interest of the user, the score is being decided. So based on the topic dispersion, so we are thinking of adding penalty. So by user, the ideal theme, P, is predefined. So here, the contents already been offered for the user. So we have additional one article, then the contents distribution being displayed. So how distanced from the ideal P can be understood, and based on that, we are able to apply penalty. To give the image of the behavior, it looks like this. So on top, there are many articles being listed. So in that case, so this is a particular article. So in that case, there is a penalty which is big. So relatively speaking, the ranking is going to be lowered. On the other hand, the medium interest article. So because of the medium interest, so it's been pushed away from the duplicated contents, and this contents was not displayed. And so it's a totally separate topic. So the penalty is relatively lower for this article, and the ranking is being increased. And so this is going to come in the middle of the duplicated contents. So based on that, so if there's a chunk of the similar contents, duplicated contents, so based on the totally different topic of contents, we are able to diversify the list of the articles. But if we use this methodology, then there's going to be a big volume of calculation. So for the skip-based one, so we are able to put the score once, and whether we are going to make skip or not based on the score is something we need to apply. But the re-ranking based on the diversity, so whenever one article is decided, then the penalty is going to be changed. So we need to do the score calculation once again. So in consideration of the volume of the calculation, so based on the effectiveness, so we are looking for the ideal trade-off situation. So next I'm going to introduce the second case example. So if there's a negative feedback from the user, how we are able to handle. So recommended article did not match with the interest of the user, then we can reduce the similar articles. So that the feedback is to be sent to the recommend system. So that function is available. So this function for the Yahoo Japan application, it's not implemented. So it's only available for the Yahoo Japan. And so in order to implement this function, so there are two requirements for the recommend model. First, so user requested to reduce the recommendation of articles. So because of that, in the subsequent sessions, we would like to reduce the number of recommendation of the article. Second one is, so the user send a signal that they dislike this article, so not just reducing that article. So what other contents to be recommended to be considered so that the quality of the recommendation is improved altogether. And so we tried two approach to overcome the challenge. The first one is when the user vector is to be trained, so users' action history behavior is being reflected. So, and at the same time, the disliked history is going to be used as a feature for the training of the user vector. So the article with the dislike signal, so if the user did not click on that article, then this recommend model is going to learn about that and lower the score of the disliked signal. So this is what the system can learn. And the next approach, so the dislike signal is input, and on top of that, like a array of the metric signal, we are going to use the disliked article directly. And so the user vector and the disliked article is going to be distanced in terms of the vector. So for the training, so they will learn to put a distance from this article. So the disliked signal is going to have a lower score. And so as a result of trying the two methodology, this is the result that we get. And so a simple addition of the input of the dislike signal. So we are unable to lower the number of articles in the same genre to be recommended because whether the user dislike a certain genre of article and whether the user clicks on the articles frequently, there is no strong correlation between the two. So even though he dislikes, but there are certain users who clicks on that article. And so the learned model, so even though they receive dislike signal, but they consider we don't need to lower the scores, so it kept recommending. And for the freight and so at negative label. So we are able to realize the lowering of the recommendation on the following. So if we do not give a consideration to the dislike signal, so the possibility that the similar article is being introduced is 30%, but by using this methodology, we are able to reduce that to 10%.
On the other hand, as mentioned earlier, users click on some extent on articles of the same genre that they dislike, so that number of clicks was reduced due to lost opportunity. So both of our approaches so far have not worked very well, and we are considering two reasons for this. One is that the definition of similar in the phrase reduce similar articles was very vague. For example, the user who clicked the reduce button for this article may not be interested in movies, or the user may have liked the movie but disliked the actress. So if the latter is the case, it would be a mistake to reduce the movie article for this user. So instead of simply saying reduce, we need to correctly read the user's intention by receiving more specific signals, such as reduce the number of articles about movies, reduce the number of articles about this actress, reduce the number of articles about this medium, and so on. Another reason it didn't work is that the current ranking approach would either keep or delete that genre. So there's only two options for that. For example, if you like baseball very much and read articles about it often, you might get a recommendation result like this one. Then you will think to yourself, I like baseball, but I would like to see other articles recommended, and you will probably hit the reduce button. Then the next time you use it, all the baseball articles will disappear entirely. So as shown in this figure, a situation in which some baseball articles are retained, while other topics are mixed in, may be what users want. However, while the approach of ranking by interest may lower the score of the genre as a whole and prevent it from being recommended, and it is theoretically impossible to reduce the percentage of articles in the same genre by a moderate amount. So in other words, we believe that the distribution-based re-ranking method mentioned in Diversification is necessary to correctly achieve the dislike signal. So we need to look at distribution-based re-ranking in order to deal with this situation. So while I have presented two examples related to user experience, I will now conclude with one example of a trap that is often overlooked in learning systems. This is a pitfall caused by the fact that when learning is performed based on random initial values, the accuracy varies depending on how the initial values are chosen. This is a story of one A/B test that we conducted. In this test, we experimented with a model that added new features to the recommended model. However, we knew that the added feature would only affect a small percentage of users. In the first test, the test bucket with the added new features produced slightly more clicks as expected. However, at that time, for operational reasons, we did not immediately apply these features to production, but only added to the release list for later use. And after several months had passed, and then we conducted a second A/B test to verify the result before going into production. So there was some interval before going into production, so we conducted second A/B test. And this time the results were reversed, with more clicks coming from conventional model, which did not include a new element. So why the result being reversed? So I'll discuss the result of more in detail. So in these figures, think of the blue boxes as users assigned to the control bucket and users assigned to test bucket, respectively. The smaller box in the lower right represent the users affected by the features added in the test bucket. And the darker the color, the better the recommendation accuracy for that particular user. In the control bucket, even the users in the lower right corner does not use any additional features, so the entire bucket is the same color. But on the other hand, in the test bucket, the users in the lower right corner is painted in a slightly darker color because he or she was able to get a highly accurate recommendation. So if this figure looks like this, the test bucket should win by a small margin as it did in the first test. However, when we analyzed the second test, we found the following. In the test bucket, the users affected by the added features performed better than users not affected by added features in the first test. However, the performance of the control bucket was higher for users who are unaffected by the added features, which should not have made any difference. Therefore, we concluded overall performance of the control bucket was better. So reason why a difference was created where there should not have been a difference was found to be due to retraining of the models. When each model was trained during the first test, the two bucket models were almost equal in performance except in areas affected by the additional features. However, since there was an interval before the second test, both models were retrained using the latest training data just before the second test. So in this case, the model on the test bucket side was unlucky in drawing the wrong initial values, so the accuracy was not as high as expected, and the base model, which has nothing to do with additional features, was inferior to the control model. So the lessons learned from this case are as follows. So it may be a matter of course, but models using neural nets have random numbers used for initialization, which may affect accuracy of the model. In particular, when verifying the addition of a function with a small impact, the overall random number blurring may be more dominant than the original function to be verified. And the difference due to the addition of the function may not be seen. After this incident, we have established a mechanism to train a model several times with multiple random numbers and select a good model to use, even if the model is automatically updated on a regular basis without changing parameters or updating the structure. So this is what happened in this case. So since this time, the regular model or retraining, we do it only once, or we do not do it once, but we do it several times to use different models and compare accuracy and choose the best model to implement in production system. So this is it from my presentation. So in this presentation, I introduced an overview of a news recommendation system at Yahoo Japan and presented 3 case studies of practical challenges and countermeasures. That's all. Thank you. Thank you very much.
So Okura-san, thank you very much. So from here, we would like to invite the questioner. We would like to dig deeper inside the presentations or the sessions with the questioner. So we would like to ask a question from the viewer as well, as much as possible. So if you have any question, please press the question mark at the right bottom to post a question. So questioner is Mr. Junki Ishikawa from LINE. So Ishikawa-san, please introduce yourself briefly. Thank you very much for your presentation, Okura-san. So I'm in charge of ML development team at LINE. My name is Junki Ishikawa. So usually, like a recommendation for the line stamp and the library used by many ML engineers and platforms, so I'm engaged with those activities. And so this presentation from the system side and ML side, we are able to listen very interesting presentation from those perspectives. So I would like to ask a question. Can I start? Please go ahead. So first of all, as for the system that you have covered in the early part of the presentation, so user vector and item vector to be prepared. So to do the vector search, so that's a deep learning. So we are able to see these technology here and there, but if we have a macro updates, so embedding, so there is no compatibility. So what is going to be the operation you do when release comes? Thank you for asking a question. So as you pointed out in your question, so here, whenever we do the retraining of the model, so if we do the training from scratch, then the space of the vector that is created is not going to be compatible. So using the same parameter and using the same dimension for the retraining, even with that, the series of the dimension is going to be piecemeal, totally different, and the space is going to be totally different. So that's easy to understand. So the different space vector model to be used for the search engine in a mixed manner. It's going to cause confusion. So for the system operation, we need to avoid that situation. So for that, so vector search engine. So we always prepare 2 systems for the search engine. So one which is referred from the production and one for the preparation is being prepared. So the vector model that is currently used, so the result of the extraction is to be fed back to the production search engine, and separate from that, the retraining to be input next. So the next version model is on hold. So it's going to be placed to the vector engine, which is on hold. So whenever the posting of article happens, we are going to put that there. So the freshness is very important for the news article. So it's just 1 to 2 days. So for us, after 8 hours passed, then the article expires. It's no longer listed. So after the lapse of time, then from the new feeding one, the vector from the old old feed is going to go away. So it's only the new vector to fill the line. And so if that happens, the system that is referred by the user is going to be switched over to the second search engine. So we are able to separate the 2 space. So from the user perspective, so instantly it's going to be updated with a new vector engine, vector articles. So for the developer, they use the 2 system. The green deployment model is used. So when I explain, then they have a clear idea. Thank you very much. So system like this is big, so it's going to be quite difficult. It's going to be complicated. That's what I thought, but I was able to clearly understand. Thank you. So this is an internal situation, but for that we had failure once. So the vector space inside. So we did switch over before the total switchover happened. So the recommendation was broken. So it's a totally different article being recommended for users. So those are the failure we had in the past. Thank you very much. Understood. Another question from the model perspective. So dislike signal handling and so the deduplication included. So we want to increase the diversity of the recommendation. So you have come up with the idea to achieve that. So evaluation of the diversification. So we tried once in my department. So based on what criteria we can call it diversified. So there are many aspects to consider. So at Yahoo Japan, how do you evaluate the diversification being achieved? Okay, so how we do the evaluation about the diversification. So we have 3 different indices to be defined. Whenever we do test and on daily basis, we do monitor based on that. So one of the indices is, so I think you can understand this, but genre to be allocated to article like baseball, soccer, politics, economies. So how the genre is diversified. We are not oriented to a single genre. So this is one indices we are monitoring. But if it's just that, the granularity is not detailed enough. So maybe the high school baseball and the professional baseball might be different, and the Japanese baseball and the major league overseas can be different. And so there are similar genre and distance genre. So for us to be more detailed, so the vector for the deduplication, the article vector, so how diversified it is something we are monitoring too. And for that, so there's an external company who is writing the academic paper, so there's a GS score being applied. So we apply that for the monitoring. So to give a simple idea about this, so the article vector based on norm 1, we are going to hold it. And the contents that's shown here, so if there's 10 articles, then the 10 article vectors, the important vector is going to be defined. So if all the vector looks at the same direction, then the norm 1 vector who is pointing the same direction, if we take an average, then norm it remains 1 if it's the same article. But if there's an opposite looking vector or so with a different direction, then we combine everything and divide by the number of vector. So and consider the center of gravity. So it's going to be less than 1. So if norm is 1, it's totally the same contents, and if it's close to 0, then it's diversified. So this is considered as one indices. So last but not least, the third one is like a natural language processing technique related. So from the article, the name of the specific things is being extracted, and we are seeing how duplicated it is. So in case of baseball, the Shohei Ohtani's name, it can come in a duplicated way. So from the article, we take the name of the person, the proper person. And so we are able to extract that these articles are talking about the same thing. And so the proper noun. So how much the proper noun is included from the article is being checked. So usually if it's 2 to 3 articles, then it's talking about the same personality or the same things. But if there are 10 or 20 in the same article, there's a problem. So we are monitoring that situation. Thank you very much. So like a MLP diversification and the harmonized filtering vector, how diversified it is. So based on that, you are measuring how it is diversified, right? And especially if the diversity is gone and if it's identical, then we are able to detect that looking at all the indices, but based on a different timeline. So what is a good one? So not just based on the indices, we don't understand that. So the people's feeling is a compound.
Therefore, there's no only one index you can refer to. We need to hit the right balance between different index. So that is actually one of the pain point that we have right now. Okay, thank you very much. So maybe you see an increase in the click, but if you look at qualitative analysis, maybe the result is so good. Well, this is actually a trap in machine learning. So if you decide on metric, then that is optimized for the machine, then you see some result. However, that is not what you want usually. Well, that is often happens. Therefore, for example, increase or decrease the first index, and after you experiment it, you need to verify once again that what you're doing is exactly resulting in what you want. So in providing a real service, we have to do a lot of those testings. Well, thank you very much for your active discussion, but we need to close now. So it's time to close.